So before introducing you to what do we mean by implicit renormalization approach, let me introduce my collaborators. Nikolai does need an introduction, and Andrei Chibukov, I believe almost everyone knows him. So what is the statement of the problem? In the vast majority of cases, superconducting transition takes place from the state of Fermi liquid. For kind of vast majority of materials, we are not dealing with a kind of non-trivial fluctuational theory of the superconducting phase transition, apart from a tiny region close to the critical temperature. But we are dealing with something which is very reminiscent of textbook BCS theory with weak interaction. However, we should understand that in essentially all realistic systems, this BCS regime is emergent rather than microscopic. It's a result of quite a non-trivial renormalization of the microscopic repulsive interaction due to the Coulomb repulsion, and then some phone slight attraction which actually changes the repulsion a little bit. So it's quite a non-trivial physics which is hidden behind the effective BCS theory. Now, at the level of effective weakly interacting theory, the physics of BCS, emergent BCS regime, can be captured by diagrammatics. The topic of our workshop is Diagrammatic Monte Carlo, by which we essentially mean microscopic approach, first principle approach, and the idea is the goal of this work is actually to utilize Feynman diagrammatics to bridge the microscopic, typically strongly correlated situation in real materials or strongly correlated models with effective weakly interacting theory, and essentially obtain the critical temperature to start with as a typical observable to obtain the critical temperature. So let me start with reminding you the diagrammatic language of how we approach the problem of Cooper instability using diagrammatic language. So essentially we can add, it's convenient to add an infinitesimally small term to the Hamiltonian, which would explicitly break corresponding U1 symmetry in this or that pairing channel. And as a result, we will have an infinitesimal linear response. So this eta, or this symmetry breaking field eta, is small, and this response is infinitesimal. Diagrammatically, this response, which looks like the anomalous average, but there is nothing anomalous once the symmetry is broken by hand, that's the diagrammatics. So essentially, in the linear approximation, well, it's not an approximation, it's a linear limit because our term is infinitesimal. The quantity, the linear response of interest, consists of two terms. So this term of the Hamiltonian, which essentially seeds this quantity, and the rest is diagrammatics. So those guys, those two lines are the Green's functions. The bold lines correspond to the genuine Green's functions. This gamma is the four-pole object which is irreducible in the Cooper channel. So we cannot cut this guy into two pieces by cutting just two lines like that. And this is the same quantity of interest, so everything looks like a linear equation with respect to this response function. And if we write it down as the linear equation with the right-hand side, and then ask a question at which point the response becomes singular, which will be precisely the critical temperature, at which essentially this theory falls apart because the response becomes singular, and the response becomes singular because this object, think of it as a matrix acting on this vector psi, and the matrix would have an eigenvalue which is 0. But since our matrix consists of two pieces, the one is trivial, essentially the unity matrix, and another one is non-trivial. So the moment this second guy has an eigenvalue which is equal to 1, the whole thing in the left-hand side, the matrix in the left-hand side, will have the matrix element 0, and this is precisely the instability. So everything boils down to the following problem. Now we can safely forget about our symmetry breaking term, because everything essentially boils down to the following problem in terms of the eigenvector and eigenvalue. So essentially there are no approximations. The only reservation which I want to make is that for the fluctuational theory, this language is not particularly special, nothing particularly convenient, but in the case of emergent BCS theory, this is precisely what we need. Essentially, the objects of interest are this gamma and those Green's functions. Now, what happens if we are dealing with the emergent BCS theory? We essentially are interested in the long wave limit. So we exclude from the theory the large frequencies and large momenta. So that's why this gamma has this bar. So essentially it's the long wave part of the gamma, something close to the Fermi surface. Correspondingly, the Green's function has the typical Fermi liquid ansatz, which I'm pretty sure you're familiar with. And essentially, what is important about this limit is that in this limit, I should make a reservation that with the Coulomb system, with its non-trivial long wave tail of the Coulomb potential, even this thing is still questionable, and we need to figure out whether it works or not. But for some kind of simple model, like Hubbard model with local interaction, this is a natural log wave limit when gamma becomes structureless, essentially temperature and frequency independent. Correspondingly, the eigenvector is also essentially structureless, and all the temperature dependence of this eigenvalue lambda comes from those two Green's functions. So if we do the integration here, we'll see that the temperature dependence essentially comes in the form of a certain log of inverse temperature with a certain scaling constant. And here is the typical BCS ansatz for the critical temperature, some prefactor, and some dimensionless small constant in the denominator. So be it a macroscopically weakly interacting theory or emergently weakly interacting theory, we have a small dimensionless number G, coupling constant G, and the temperature gets exponentially small in terms of this effective coupling parameter. Now comes the question, can we essentially promote this very simple, very visual theory of Cooper instability to the microscopics? Can we actually start with diagrammatic Monte Carlo microscopically and end up with something in which everything in this formula will be calculatable? That's essentially the program, and that's the statement of the problem which we had in mind quite a while ago. We were discussing with many people here in the room, so how to properly actually do the theory so that we can essentially start with microscopics and end up with effective BCS theory. So it's actually convenient to change a little bit, to improve a little bit notation. So rather than dealing with this function which we introduced before, it's convenient to introduce this so-called gap function delta, and here is the definition. So essentially, if we sandwich this new function delta between two Green's function, we are supposed to get this response eigenvector which we introduced before. So this is essentially the definition of the gap function, and in terms of the gap function, we just rewrite the very same eigenvalue eigenvector equation. Now the gap function is essentially eigenvector which we are looking for. We rewrite it in the following form. So now with this rewriting, what happens, we just change a little bit the kernel which acts on our eigenvector delta. So this kernel consists of the bare Cooper irreducible vertex gamma and two Green's functions. And we want to see whether we can do something about this problem by calculating. So the idea is that we calculate gamma We calculate gamma diagrammatically by diagrammatic Monte Carlo. We calculate G diagrammatically by diagrammatic Monte Carlo and somehow solve this equation. By the way, this equation can also be solved diagrammatically because this is a typical situation with so-called bold diagrammatic Monte Carlo, when some unknown, in our case delta times lambda, is expressed in terms of itself. So if you're familiar with bold diagrammatic Monte Carlo at the level of some basic problem like a scattering amplitude, this is kind of, we can call it a textbook, a typical problem to solve diagrammatically, provided you know how to simulate this kernel. So essentially we are talking of two separate processes. One process would simulate this kernel, not even histogramming the function gamma, but just producing corresponding set of variables. And then with the tools of bold diagrammatic Monte Carlo, we will essentially sample the left-hand side of this equation, this product. But since, so the only difference with the kind of bold diagrammatic Monte Carlo which we discussed so far is the normalization. Since it's a linear equation, there is a free normalization. So if we pick up some normalization for our vector, doesn't matter which one, then essentially we will be always normalizing our delta when we will be plugging it into the diagrammatic Monte Carlo process in the right-hand side, and the process itself will be producing the left-hand side, and then we will just compare the normalization of the left-hand side, and that's how we will extract lambda. So protocol-wise, everything is very straightforward. However, there is a problem, the problem of convergence. We cannot just typically we cannot run this simulation down to the critical temperature because of convergence. So typically the process would not converge at that low temperature. Moreover, we do not want to do that, because if we go to extremely low temperatures, we have a huge range of frequencies. We really want our actual goal is to extrapolate. Somehow we want to extract all the information from temperatures which are clearly much lower than the temperature, than the Fermi energy, and also much lower than any energy scale relevant to the renormalization. However, we want to be exponentially higher than actual critical temperature. And it turns out that this simple physically understandable setup, because physically we understand that, at least at the level of effective theory, that we do not really need to go to that low temperature. My previous slide, we remember that actually the logarithmic behavior sets up much earlier than we reach the critical temperature. So essentially physically everything is clear. However, the problem is that if we will be solving precisely this equation for the eigenvalue lambda, and we will try to extrapolate lambda of t which comes out from this problem at high temperatures, we will fail. And that's essentially what I want to understand, to explain on the slides which will come next. But before embarking on this explanation why we will fail with just naive extrapolation of this lambda, I will just take a different course of action. First of all, I explain how to proceed properly, and only then I will explain why there is no way around, why there is no way around proceeding the way I will be explaining. So rather than solving this problem, rather than essentially doing this renormalization, probably at this point I want to introduce to remind you the idea of renormalization. So I already mentioned the term, but explicitly renormalization precisely means the following. So this gamma bar, which I introduced before, is nothing but a sum of the ladder diagrams. So this is the bare gamma. And if we sum the ladder diagrams such that we exclude the low energy part from those two Green's functions, so it's a ladder, but a ladder in which the low energy part is excluded, this is essentially the definition of this effective vertex gamma bar. And the first question might be, why don't we just do this renormalization explicitly, because it's so simple in the emergent PCS regime. The problem is that it's simple as long as we write it diagrammatically like that, but if we want to do it numerically, we face what we can call the curse of multivariableness. So those guys, gamma bar and gamma, are multivariable functions, and it's problematic even to histogram, even to histogram gamma, putting aside the problem, a non-trivial problem of essentially solving this multivariable equation. So while everything sounds very transparent at the level of definitions, numerically we cannot implement this protocol explicitly. That's why the term implicit renormalization. So essentially it turns out that rather than solving this problem explicitly, rather than explicitly obtaining a gamma bar, we can actually set up a problem in such a way that without actually even producing gamma, without even producing gamma bar, we will be able to extract the main quantity of interest, lambda bar, as a function of temperature. So in effect, we will solve the effective theory without essentially explicitly renormalizing the interaction. This is the main achievement of essentially the work which I'm presenting, as long as we are talking of diagrammatic Monte Carlo. So let me just make a few preliminary steps and introduce the matrix vector notation for the problem. So it's a shorthand notation. So essentially my vector, which is a function of momentum and omega, I will be denoting as just a vector, and my kernel and integration will be just replaced with this matrix. So this is our original problem. And what I will do at this point, without changing anything, I will just separate my vector into low energy and high energy pieces, delta 1 and delta 2. So we just pick up some condition. In this case, I pick up the condition which is based on the frequency and the dispersion. This psi of p is the dispersion, and require that the low energy part is identically equal to 0 when this condition is met, and omega sub c is just some energy scale. We will see that it's essentially, there is a range of scales, so it's not just some particular number, but it's a range of numbers, and the answer is not supposed to be sensitive to the choice of this guy if we are in the right range of energy scales. Similarly, the high energy part is supposed to be identically 0 when this combination is smaller than omega sub c. In principle, so it's a matter of convenience. It depends actually on the structure of the kernel. We can even exclude the dispersion from this expression and just work with omega. It will be sufficient. It's a matter of convenience of a given protocol. The key role is played by omega. So essentially we want to separate omegas in the high and low energy part, but it might be convenient to also involve the dispersion. Correspondingly, this operator matrix has 4 separate pieces, like the piece 1,1 deals with the low energy part, the piece 2,2 deals with the high energy part, and we have 2 pieces which mix low energy and high energy parts. And just rewriting the original problem in the new notation, we have this system of 2 equations. And what we do with this system, we just replace it with a new one. So what happened here, I took this system of 2 equations, which is just equivalent to the original one, and by hand replace this lambda with just unity. And what we observe, first of all, the first observation is absolutely straightforward. Since the critical point corresponds to the lambda equals to unity, we understand that in terms of the critical point, those systems are absolutely equivalent. However, and most importantly, if we go further and analyze what's written here by excluding actually delta 2 from the second equation by this formal substitution, which formally solves the second equation, and then plugging this expression into the first equation, we see that with respect to the low energy part, delta 1, we have the following equation with the following actually operator. And if we look carefully at this operator, we see that this operator is nothing but the ladder diagram, not even the ladder diagram, but just this. Of course, we can expand this expression into the ladder diagram, but essentially this operator is nothing but the formal solution for the gamma bar times 2 Green's function. So essentially this operator B is nothing else than the kernel of the actual effective theory. So by this formal procedure, we understand that this system, in terms of the eigenvalue lambda bar, is equivalent to the effective theory. And this is all we need, because after all, we need the effective theory to extract lambda bar, and we just demonstrated that this lambda bar is nothing else but the lambda bar of the effective theory. So essentially this solves the problem, and the next few slides will be just the illustration why this solution is crucially important as compared to the naive extrapolation with the eigenvalue lambda, which comes from solving this problem rather than that one. So essentially we will consider the models which are dramatically simplified in the sense that our kernels will be momentum independent. So we will confine ourselves to the formal models, just they are not microscopic models, but just some kind of postulated effective models with the same structure, such that there is no momentum dependence in the kernel. The moment, well, in gamma it's better to say, the moment there is no momentum dependence in the kernel, in the four-pole object gamma, the gap function becomes momentum independent. So it's just some function which depends on Matsubara frequencies. And with the Green's function of the following form, with the linear dispersion, so the integration over momentum in the kernel can be performed explicitly, and the bottom line is the following eigenvector, eigenvalue equation for the gap function. So far, it's kind of think of this equation as if it's some microscopic equation. It's not an effective theory. It's just some very simple microscopic theory with a certain function B, which depends on two frequencies, and this omega in the denominator is just the result of integration of the Green's function over momentum. And we start with the most simple Ritschl-Chem model. So this model, the explicit expression for the function v in this model goes as follows, but it's better actually to look at this plot. It's even simpler. So the idea of this model is the following. There is a certain energy, E sub c, beyond which this interaction is just identically equal to 0. And there are two very simple regions. The region below EC in this square, when the interaction is just a certain constant g, and a smaller square defined by the characteristic frequency omega, when actually the interaction gets somewhat small. So this formula means that there is some interaction which slightly reduces this g by a certain factor, which is supposed to be positive and smaller than unity. So this is kind of the essence, the simplified essence of what happens in real materials when at the microscopic level the interaction is all repulsive. So there is no attractive part. Think of it as if we have a microscopic bare Coulomb interaction, which is obviously repulsive, and on top of that, we add a tiny, compared to the Coulomb interaction, phonon attraction, but the sum of the phonon attractions, think of this F, think of this vector F as if it's coming or kind of modeling the phonon attraction. So if we sum up the two, obviously we still have a repulsive interaction, and the whole idea of this type of the overall interaction is that it's retarded. It's retarded in the sense that it's there is a substantial frequency dependence. So the whole effect, which essentially mimics the effect which we are dealing with in real materials, is that the phonon interaction is retarded as opposed to the instant Coulomb interaction, and it's the retardation which ultimately results in the effective attraction in the Kuiper channel. So physically it's very non-trivial, and what's amazing about this very simple model, that this non-trivial physics is perfectly captured by this very simple model. So what's very simple about this model is that it's immediately solvable, because the structure of the frequency dependence is separable. And the bottom line is that the eigenvector delta is parameterized by just two numbers, A and C. So it's nothing else but the two parametric piecewise constant function. So we have just two constant pieces and identical zero at frequencies above EC. And the whole problem immediately, the integral equation immediately reduces just to a system of two algebraic equations. The system can be solved, but I do not need to write down the solution here. I will just show two plots on the next slide. But what follows, what we are going to see on the next plots, is that the dependence on this lambda on the log of temperature is very nonlinear. So the temperature dependence in this problem comes from this capital letter L. Nothing else depends on the temperature in this problem except through this parameter L. And essentially, in terms of this model, our implicit renormalization formulation is also very simple. As you remember, in the second equation, we are supposed to replace lambda with just 1. So what's good about this model, there is a natural choice. You can say good or maybe not very good, given that it's very special. So in this model, we clearly see what should be the choice of the typical energy separating the high frequency part from the low frequency part. It's just this frequency omega, so it's a very natural choice. Of course, we can use a different choice, but then the algebra will become more complicated. That's why we just confine ourselves with this natural choice, when the high and low frequency omega are just those two pieces of our piecewise to parametric piecewise function. So that's the algebraic equation, which is immediately solvable by essentially expressing A from the second equation and plugging it into the first equation, and we end up with the following bottom line, which is very kind of transparent physically. So first of all, it's a trivial expression in which we see that the eigenvector S, remember that it essentially represents the low energy part of the effective theory for the gap function, stays constant. It's temperature independent. And essentially, there is a factor in the right-hand side. Actually, there are two factors. One is a temperature-independent factor G, call it effective interaction. Here is an explicit form for this effective interaction. And the temperature-dependent factor L, and we immediately see that our eigenvalue lambda bar features the desired linear dependence on this log. This is precisely the goal we wanted to achieve. We wanted to see a very straightforward flow with temperature of our eigenvalue lambda. We see it, and also physically this is a very interesting combination, because if we analyze the structure of this expression, we will see that this effective interaction can be positive and can be negative. So this very simple model features two regimes: the regime of Cooper instability and the regime of the absence of Cooper instability. So let us just see.
Boris?
Yeah.
Just 3 minutes.
Yeah, I'm almost done. Yeah. Right, before the discussion, right? So
well, I mean,
okay.
You've already gone into discussion time.
Okay, right. Oh, I see. Because I was thinking that you added me. Okay, because I was keeping in mind. Yeah, okay.
No, I took into account
right.
the fact that we started late.
Right. So essentially, that's the bottom line for this model. So if we do the bare lambda, if we just solve the bare problem for the eigenvalue, we see absolutely no difference between Cooper unstable and Cooper stable cases. So this case is Cooper stable. There is no Cooper instability, and in both cases we see, depending on the choice of our parameters, we see more or less the same nonlinear scaling of lambda, and we understand that this scaling is nothing but misleading. We cannot conclude anything from this lambda of T before we go really close to the critical temperature, and with a lambda bar we see everything nicely, just a linear behavior. So if we take a less idealized model, in which case we have to play with the separation scale omega, we see pretty much the same behavior. We see that in terms of the original lambda, it's a nonlinear behavior. In terms of the lambda bar, in terms of implicitly renormalized theory, we have this nice straight line behavior. We see how to properly choose the separation scale omega sub c. So we see that within almost a decade of different choices of omega c, we reproduce by extrapolation one and the same value of temperature, so everything is working. So this model is essentially pretty much the same as before, but with a smooth transition from high frequency to low frequency behavior. And essentially that brings me to the concluding remarks. So essentially we understand that there exists a protocol of extrapolating data from high temperatures to low temperatures. This protocol, however, is not a straightforward eigenvalue problem in terms of the bare gamma. We need to do implicit renormalization. The scheme is free of any systematics apart from the extrapolation, but the extrapolation is a controlled systematics, as I was explaining in this plot. So essentially we do control our error bars. The scheme is perfectly compatible with diagrammatic Monte Carlo, and what I didn't tell you, but maybe it's also clear, that from the very same protocol we can extract not only the renormalized eigenvalue, but also the eigenvector, and actually we can extract the critical structure of the gap function as well. Thank you very much.